In this chapter, we will be introducing the concept of integration. In this video, we will be looking at the area between curves.
Hi everyone. So in a previous lesson we looked at how to find the area under a curve, okay, using calculus, using antiderivatives. And now we're going to do the natural next step here, and we're going to look for the area between curves. So again, just to kind of reiterate what we've done thus far, here's my x, here's my y, okay? If I've got a function, I don't know, let's say something like this, and let's say that this is my f1 of x, okay? I can determine the area beneath this curve between a and b, okay? Because this particular area function here, remember how this works. The derivative of the area function is going to equal the function that we're finding the area under. So I can figure out the area between a and b, and remember how we did that. We then took the antiderivative of f and then we subtracted it. We went from f of b minus f of a, assuming there was some arbitrary endpoint with our function here that ended up getting rid of our arbitrary constant. Now, another thing that I could do here is I could have another function here, okay, and let's say that this is my f2 of x. Well, I could find the area underneath f2 of x as well, okay, and so this area function right here, the derivative of it is going to equal f2 of x. And now remember how that works. So the area of our underneath our f1 is going to be right down to our x-axis. The area underneath f2 is going to be right down to the x-axis. So if I wanted to know the area in between, okay, well that area down in between there is simply going to be equal to a1 minus a2. And in fact, that's how we're going to approach this problem of finding the area between two curves. So let's just jump in and take a look at a couple of examples. All right, so our first example here tells us to find the area of the region between y equals 2 minus x squared and y is equal to negative 2x plus 3. And we're going to find that from between the x values of negative 1 to 1. And just like we've done in the past here, I think the best way to start this is to graph it, to actually have a look at what it is that we're finding the area of, or at least see what that area looks like. So 2 minus x squared, okay, is going to look something like that. Okay, so here's my y is equal to 2 minus x squared. And that negative 2x plus 3, well, that's going to be a linear function. It's going to drop down. And actually, I've looked at this already, and so I know that there's going to be a point of intersection right there. And actually, it turns out that point of intersection is going to be at positive 1. And so back here, we've got negative 1. And we're going to figure out the area, okay, between these two curves, but between these two values of x here. And I hope that you see that it's going to be this shape right here. Okay, that's what we're going to find the area of. Now, it's again, this is kind of a neat to think that you were going to be able to find the area of this fairly strangely shaped object here. Okay, now we're going to do this in using two different methods as well here. So method 1, it's going to look like this. What we're going to do is we're going to find the area under negative 2x plus 3. And we're going to find the area under 2 minus x squared, and then we're going to subtract them, okay? So let's take our area function here. We know right now, okay, that the derivative of my first area function here, or my first function here, is going to be negative 2x plus 3. Okay, that's the function that's on top here. Maybe I should just label that here. That's going to be y equals negative 2x plus 3. And so now for us to take the antiderivative of that to get our area function, I'm going to increase the exponent by 1. It'll be 2 divided by 2, so the 2's will cancel. So this will be negative x squared plus 3x plus c. Now, remember, I don't really need to worry about that plus c anymore, because that plus c is there because I could be coming up with the area function relative to some left-hand starting point. But because I'm going to find the difference between those two functions, between these two x values, I don't really need to worry about that. So I'm going to take my area 1, I'm going to evaluate it between -1 and 1 along this interval, which means I'm going to evaluate it at 1, and I'm going to subtract it, evaluate it at -1. Now, when this is all said and done, okay, this is going to end up being, what is it, -1 plus 3 plus c minus -1 minus 3 plus c. Okay, plugging in the 1, plugging in the -1. Now remember, the -1 over here is going to cancel because of the square, but there's still a negative in front. And when all's said and done, I get 6. Okay? Good. Now what we're going to do is we're going to do the exact same thing, but this time we're going to do it with the other function, our second function here. We're going to let a2 primed be equal to 2 minus x squared. And actually I have run out of paper, so I'm going to flip over to the other side. Oops, did I do that right? Yep. Okay, and so my a2 prime, I'll write this out again, is going to be 2 minus x squared. And so now I will take the antiderivative of this to get, that will be 2x minus 1/3 x cubed plus c. Now this is a different constant than what we just saw in the previous expression here, but for what I'm about to do here, I'm going to find the area again between those two endpoints, so that the plus c is going to disappear anyway. So I'm going to evaluate this between -1 and 1, and so that is going to be 2 times -1 minus 1/3 times sorry, I should be putting positive. I'm going to put +1 there. It should be +1 minus the -1 there. Okay, we go right-hand side minus left-hand side, so it's going to be cube plus c minus, now this will be 2 times, here's where the -1 goes, minus 1/3 -1 cubed plus c. Whoop, gone off the screen there. Okay, and then when you finally evaluate all of that, you'll find that you're going to get 10/3. Now, that means that the area that I'm looking for is going to be the difference between those two. It's going to be a1 minus a2. Now in this case it's going to be 6 minus 10/3, and when you put that all together you're going to get 8/3 units squared, whatever those particular units are. So there we go. The area of that almost kind of, what is it, like shark finned shape almost, is going to be 8/3. Now there is another method that we could employ to do this. Okay, and so method 2 is going to look like this. What we did in the previous example here is we found the area underneath each function and then found the difference between them. But because of the way the antiderivatives work, because you're doing it term by term, okay, and each term is basically separate from the others here, it doesn't really matter what order we go about doing this. So another thing that we could do here is we could actually create an area, the overall area function. So here, our overall area was area 1 minus area 2. And remember, each one of these, okay, was the antiderivative of our function here. Well, what we can do is we can create the overall area function right off the bat, okay, and make its derivative equal to f1 minus f2. And so we can actually set up that subtraction prior to the antiderivative. And so now what we'll get here is our antiderivative function here is going to be, the antiderivative function. Our area function that we're taking that we've got the derivative of here is going to be -2x plus 3 minus 2 minus x squared. And what we'll do is we'll do the subtraction first. And when we do this and then reorder the terms, we get x squared minus 2x plus 1. Okay? Now, this is a kind of a new function here. It's related to the two previous functions, but it is a brand new function. We're now going to find essentially the area under this function, with the understanding that that area is going to be equal to the area that we've just outlined before here. So now area is going to equal 1/3 x cubed minus x squared plus x plus c. Okay, so we take the derivative of each term there. We still got that arbitrary constant. Now what we'll do is we'll evaluate this function on the interval -1 to 1. So that's going to be 1/3 of 1 cubed minus 1 squared plus 1 plus c minus 1/3 times -1 cubed minus -1 squared plus -1 plus c. Whoops, and I know that's gone right off the screen there. And when you put that all together, lo and behold, you get 8/3 again. 8/3 units squared, whatever the units are. So there you go. There are two different methods that we can employ to find the area between two curves. You can either find the area underneath each one separately and then do the subtraction, or do that subtraction right off the bat to create this brand new area function derivative, and then take the antiderivative to get the area function back here. This is probably the method that we're going to utilize from this point on, though. All right, let's now apply what we know, and let's find the area between y equals 4 minus x squared and 2x minus y plus 1 is equal to 0. Now, probably be easier if we recognize that this was just going to be bring the y over 2x plus 1. Okay. Now, let's take a look at what this particular scenario actually looks like. So 4 minus x squared is going to be, I don't know, is going to be something that looks something like this. It's going to be a parabola that opens down for sure. And then this 2x plus 1, now remember this is going to be about 4 here, so 2x plus 1, that's going to be somewhere down here. And it's going to have a slope of 2, so it's going to look something like this. Now, what we're looking for is always the finite region. So, like, don't extend this line and then find the area between the line and the curve here. We're really just looking for this piece right here. Okay, we want to find that area. So now, and I'll just label the graphs here. This is going to be 4 minus x squared, and up here this is going to be y equals 2x plus 1. What I don't know, and what I need to know, are what these x coordinates are. Okay, I need to know what it is I'm finding, basically horizontally, what the limits of this evaluation are going to be here. When I find the area under the curves, whether I do it separately or together, I just need to know basically what what function I'm going to evaluate, and then what other function I'm going to evaluate when I subtract those. So the first thing I got to do is find those points of intersection. Okay, where those two graphs meet here, and that's actually not that hard to do. Okay, so this is going to be 4 minus x squared, and we're going to set that equal to 2x plus 1. Well, this is nice. I'm going to bring everything over, make that x squared plus 2x, what's that going to be, minus 3. And that actually factors down really quite nicely into x plus 3, x minus 1. So my two x-intercepts here are going to be at, x-intercepts, the two spots where these functions intersect, is what I really meant to say, will be -3 and 1. Okay, basically those are the x-intercepts of this particular graph. So now we're going to determine what our area function is, and then we're going to take the antiderivative of that difference there and evaluate it between those two limits. So we know that the derivative of our area function is going to be the difference between those two functions. So this is going to be 4 minus x squared minus 2x plus 1. Okay, and so that's going to get us -x squared minus 2x plus 3. Now, notice the relationship between this function and the one up here that I used to find the points of intersection there, the x-coordinates of those points. That is not always the case, that it's such a nice, clean relationship there, and you really want to pay attention to that. Sometimes in order to get those points of intersection, you have to manipulate the equation a bit, and it's not what you're going to take the antiderivative of. Okay, Just something to be aware of here. So when you're setting up this a primed, it's the upper function minus the lower function here. And so now when you want to figure out what the area function is, we're just going to take the antiderivative. That is going to be negative 1/3 x cubed minus x squared plus 3x plus c. And now my area from negative 3 to 1 is going to be the area at 1 minus the area at negative 3. And so that is going to be negative 1/3 1 cubed minus 1 squared plus 3 times 1 plus c minus negative 1/3 negative 3 cubed minus negative 3 squared plus 3 times negative 3. Are we off the screen? Yep. Whoops. Whoops, and I forgot the plus c. Wait a second, 3 times, oh, I see what I was doing there. Let me just fix that real quick. 3 times negative 3 with a plus c at the end there. Now, I've already gone through and done that work there. Everything becomes 32/3 units squared. And there you go. Okay, we found the area between those two lines there. That rather interesting shape. Okay, isn't that neat? Let's take a look at another example. Okay, so this question says find the area between y equals x cubed minus x and the x-axis, or the area under the curve, if you will. Okay, now once again, let's have a quick look at what this scenario looks like. Here's x and here's y. Now, y equals x cubed minus x. If I can factor out the x there, I'm going to get x times x squared minus 1. So I know this is going to have x-intercepts here at 0, at negative 1, and at positive 1. And the graph is going to look something like that. Okay? So now when I ask for the area between this function and the x-axis, remember that I'm always talking about the finite area. So what I must be talking about here are these two little bumps right there. Okay, so we've only got the one function right now, so that's easy enough. So my derivative here of the area function is going to be x cubed minus x. So if I take the antiderivative, I will get 1/4 x to the 4th minus 1/2 x squared plus c. Okay, now I'm going to evaluate that between negative 1 and 1. Okay, negative 1 over here, 1 over here. Basically the outer limits of the finite area that I'm looking for. And when I do that, I'm going to get, remember, that I'll write it like this. This is going to be the area at 1 minus the area at negative 1. I'll just write that out like that. So that is going to be 1/4 of 1 to the 4th minus 1/2 1 squared plus c minus 1/4 negative 1 to the 4th minus 1/2 negative 1 squared plus c. Whoops, wow, I'm really off there. Sorry about that. Now, what's important to notice here is that as soon as I do that, I'm going to get 0. Okay, I'm going to get 0 for my area here. And that's because when I take negative 1 to the 4th power, negative 1 squared here, it's going to look exactly the same as this first expression, and then I'm just going to subtract them. So they're going to cancel completely. So what's going on here? Because clearly there is some area outlined here. So what am I going to do? Well, what I got to recognize here is that we've got some symmetry. This little bump here and this little bump right here are exactly the same area. And what's happening here when we find this area, our procedure is essentially creating a little rectangle, if you will. Okay, and we're going to talk about this more in a little bit. But if you want to understand what our procedure of taking the antiderivative is doing, is it's creating this little rectangle and finding the area of that rectangle. And it does that with an infinite number of little rectangles inside here. Now, over here is a little different than what happens over here. And the reason for that is because of where the function is located with reference to the x-axis. So we're always, when you're doing the calculus here, we're always moving left to right. So the width of my rectangles here is always going to be positive. That's not a problem. I'm always moving left to right here. But my height, remember that when I say area under the curve, I always mean to the x-axis. And when we build this rectangle, okay, the height of my function is represented, the height of my rectangle is represented by the function. So if the function dips below the x-axis, all of a sudden you're going to get a height here that's negative. Okay? Or, and I can extend this further here, if you're comparing two graphs, and remember how we did upper function minus lower function? If you got that backwards and you did lower function minus upper function, the difference between them is the height of that little rectangle. And if you do that in the wrong order, you're going to get a negative height. And as a result, you'll get negative area. Now, what happens here is very natural. Positive height, negative height. The areas are exactly the same. It's just that this has got a negative value, this has got a positive value. And so what ends up happening is they cancel each other out. And so what happens here is our procedure here, what we've actually done is we found the difference, okay, in the areas. Okay, we found the difference between the two areas there. Now it turns out in this case the difference dropped her down to 0 because they were identical to one another. Now, it turns out that sometimes that's actually what you want. Okay, there are going to be all sorts of applications for this procedure, this process of finding the antiderivative, or later on what we'll call the integral. There's going to be all sorts of wonderful applications of this, and sometimes you are actually interested in where you've got positive and negative values popping up. It could be, for example, that we are talking about the number of sales over a given amount of time. And let's say we've got positive sales, but sometimes maybe more people returned than bought on a certain day, and so we've got negative sales. And we're interested in what the total value is. And we are curious about how the negative affects the answer. But sometimes we're not. Sometimes we are just interested in the area. And so we don't want to find the difference in the areas. Okay, we don't want this difference anymore. But that's what this procedure is doing here. So in order for us to get the actual area, what we've got to do is we've actually got to split this up. We've got to split this up into the two pieces here. Now, we've already established that these two pieces are exactly equal to each other. So one of the things we can do is simply find the area from -1 to 0, okay, and then multiply that by 2. So in this particular case right here, what we might actually do to get our area is we will multiply, let's call this our total area. We'll multiply the area function that we get from -1 to 0 by 2. And so that'll be 2 times, and our area function here, if I'm going to do this correctly here, is going to be, that will be, what do I get here? 0 to the 4th over 4 minus 0 squared over 2 plus c, so that kind of goes away, minus, I'm going to put square brackets around that, -1 to the 4th over 4 minus -1 squared over 2 plus c. Okay? Now remember that those even exponents there are going to create positive ones there, which actually means that we could have done this from 0 to 1 and it would have made no difference. Okay, it would be exactly the same here. And when we do that and put that all together, we are going to get 2 times a quarter. And so our final answer here is going to be 1/2. So the total area there will be 1/2 units squared. The other way that we could have done this to figure out our total area would be to figure out the area from -1 to 0 and then add that to the area from 0 to -1. Now bear in mind, we've already established that this area here will be negative. So the way we get around that is we're just going to simply put the absolute values around everything, basically. Okay, it's not necessary here, but sometimes you won't know when that's happening or not here. So we're going to look for the x-intercepts. We're going to look for where the function crosses the x-axis or where the functions cross each other. Okay, because for example, if you've got two functions that are doing something like this, and let's say my other function looks something like this, and we're finding the area between them. Let's say that this is f1 and this is f2. Sorry, I'm going to put of x there. If I am simply evaluating my height by going f1, okay, if my area function is going to be f1 minus f2, then what's going to happen here is f1 minus f2, the height is going to be positive here, but it's going to end up being negative over here, okay, because f1 is below. And so you got to understand what's happening when the functions switch location vertically, and just respond to that appropriately. So in that case here, you'd have to split this up into these two intervals, and then make sure you take the absolute value appropriately.